When physicist Enrico Fermi looked up at a universe filled with billions of stars, he asked a simple question: where is everybody? If space is so incredibly vast, why do we appear to be completely alone? That problem became known as the Fermi paradox. To understand the conditions required for life, we have to stop looking at the distant universe and focus closely on our own cosmic backyard. The story of our solar system is a history defined by extreme violence and precise timing. Before any planets existed, a massive cloud of gas and dust drifted through space. A powerful shockwave from a nearby supernova compressed this cloud, forcing it to collapse inward until the pressure forced hydrogen atoms to fuse together, and our sun ignited. That newborn star immediately claimed 99.8% of all the mass in the surrounding cloud. Every planet, moon, asteroid, and living organism you have ever known was forged entirely from the chaotic collisions of the leftover 0.2%. The inner solar system is a brutal environment. Closest to the star, Mercury is a desolate rock blasted by intense radiation. Just beyond it sits Venus, trapped under a crushing carbon dioxide atmosphere and a runaway greenhouse effect, where surface temperatures melt lead. Earth sits between them, covered in liquid oceans and a breathable atmosphere. But our planet didn't form peacefully. A rogue body the size of Mars, known as Theia, slammed directly into the young Earth. We know this collision happened because of physical evidence brought back by the Apollo missions. When researchers analyze the porous texture and chemical makeup of these lunar rocks, they see the exact signature of a high-energy environment. The impact liquefied Earth's crust and flung a massive ring of molten debris into space, which eventually coalesced to form our moon. Earth acquired its life-sustaining carbon during a specific temperature window. As the solar system cooled below 440 degrees, carbon molecules solidified. If this cooling happened earlier or later, Earth would lack life's building blocks or bake in a toxic greenhouse state. The violence continued. Around 3.9 billion years ago, the late heavy bombardment sent massive, continent-sized asteroids crashing into the Earth's crust. Instead of sterilizing the planet, these impacts fractured the crust, allowing water to seep down and create deep hydrothermal vents where heat-loving microbes flourished. You can still see modern relatives of these microbes thriving in the scalding, colorful waters of the Grand Prismatic Spring today. The presence of water, carbon, and life on Earth is not a peaceful accident. It required a highly specific sequence of cosmic violence and exact temperature drops to create it. A perfectly forged planet can still be easily destroyed. Mars is a rusted, dry world that lost its early surface water to space. Why didn't Earth suffer a similar fate from continuous asteroid bombardments over the last billion years? Jupiter's massive gravity acts as an active cosmic shield, deflecting incoming celestial bodies away from the inner planets. But if Jupiter possessed a highly eccentric elliptical orbit, its immense gravitational tug would drag Earth's orbit out of shape, triggering chaotic, unsurvivable climate swings. The rest of the outer system plays a role in this balance. Saturn, with its sprawling ice rings, Uranus, knocked entirely on its side, and Neptune, battered by fierce winds. These frozen giants function as an interconnected gravitational defense system. By keeping outer debris in check, they maintain the orbital stability Earth requires. The precise orbital mechanics of the solar system have provided a safe harbor for billions of years, but the engine driving it has a finite lifespan. About 5 billion years from now, the sun will finally exhaust the hydrogen fuel in its core. To compensate for the loss of internal pressure, the star will rapidly expand outward into a red giant phase. As it swells, the intense, blinding heat will completely swallow the orbits of Mercury and Venus. For Earth, the consequences will be fatal. The rising temperatures will boil the oceans away entirely, triggering a runaway greenhouse effect that melts the surface back into a global sea of lava. The sun will eventually shed its outer layers into space, leaving behind a dense, glowing core known as a white dwarf. Long after the star dies, the dead Earth faces one final kinetic event. Tidal forces from the remnant sun will sap energy from the Earth-Moon system, causing the moon's orbit to slowly decay until it crashes directly into the planet. Our solar system is not a permanent fixture in the galaxy. We exist within a temporary sequence of cosmic dominoes, a brief, perfectly timed haven that gave a rocky planet the chance to support life, and eventually look up to wonder at the stars.
Subscribe for more videos and press the bell icon for latest notifications.